This lesson is for FST, lesson 9.3 on logarithms or logs. Students will need both a baby calc and a graphing or scientific for this lesson. There will be a mixture of both kinds of problems. Typically when I work with students on learning a new topic and there's a graph involved, I tend to put the graph at the end and then forget to talk about it. So I put the graph at the beginning here so that I wouldn't forget about it. When you're doing the graph of a log, the shape of it is pretty much going to look like this. It's called a logarithmic curve, and I want to talk about the domain and the range. The domain is referring to the x values, or the width of the graph horizontally. Notice here that this line never will cross over the y-axis. The y-axis behaves like an asymptote. So the domain here is going to be all values greater than 0 for x. For the y values, if you think about the range, vertically and horizontally, this graph is going to go down and up forever, so that's going to be all reals. That's pretty much typical for most logarithmic curves. Why do we need logs in the first place? Well, when we solve problems involving exponents, if the exponent is missing, we need a log in order to be able to fix that. We won't necessarily get into this specific idea today or in this video, but we will talk about how to solve for a missing exponent later on in chapter 9. What is a log? Well, it's basically a rearrangement of an exponent problem. And how it rearranges it is it makes the exponent the answer. So the answer to every log problem is always going to be an exponent. So because of that, every exponent problem obviously has an exponent in it. It also has a base that it came from, and then it has an answer. And what a log problem does is takes those three pieces and jumbles them up. Students need to be comfortable taking an exponential formed situation and turning it into a log and vice versa. So if we do a log for this particular problem, we write the word log for logarithm. Then there'll be a little subscript down below, and that's whatever the base is. So in this case, base b. And then the next thing that we write is the answer to the exponent problem. So in this case, that would be the x, because we want the y, or the exponent, to be the answer to the log. Notice that now the base is the number that gets minimized, and the x and the y become kind of equal partners here in this label. There are other types of logs that students need to be comfortable doing. And the next type is called a common log. Common logs have base 10. So if you're working with a log problem and there's no base given or no base listed, you can assume that it's a base 10 problem. The last type that we're going to get to in a future lesson is logs base e. If a log has a base e, it's actually called a natural log. And again, there's no base listed for those. Students need to be comfortable maneuvering back and forth between log form and exponential form and going back and forth. Students will be doing common logs first and then working with logs with other bases. You'll see some similarities and differences between the two columns worth of problems. I would recommend very highly for students, especially those struggling with logs or those who are brand new to logs, to fill in all three parts. There's always going to be a base even if it's not given. There'll always be an answer and there'll always be an exponent. So make sure you give all three parts when you're identifying a problem. Then I would recommend converting it into exponential form. So in this case, the base is 10. We're raising to the x power and we're trying to get to 100. At this point, students need to do a little trial and error and say 10 to the what is 100. Well, 10 to the first is too small, and 10 squared hits it right on the head. So the answer there is 2. Common wrong mistake there is for kids to say 10 because they think 10 times 10 is 100, which it is, but what we want to do with a power situation is count how many 10s it took to get there. Students need to watch out for decimal or fraction questions because those require a negative. Again, if you fill in the missing base and whatever else is missing, when you rewrite it in exponential form, you're going to get 10 to the what equals 0.1. If you say that a little bit more accurately as 1/10, which is what it is, the answer is a little bit easier to come up with. The 10 stays as a 10, but it does flip over to the bottom of a fraction. The only way to get a base number to flip over like that is if it had a negative number with it, or a negative exponent. Since the 10 doesn't change into a 100 or a 1,000 or a decimal, we just need a 1 there, but it needs to be negative in order to flip it over. So Those would both be baby calc questions. You wouldn't need a calculator to determine the answers for those. The next one, if you fill in as exponential growth, as exponential form, you end up getting 10 to the what is 25. Now that would not be one that I would expect students to be able to figure out without some kind of a graphing calculator. So you'd want to actually type in log of 25 on your graphing calculator and then round that off. So you could do it this way, or you could just type it in as is. Every calculator that's scientific or higher does have a log base 10 button on it. On the Inspire calculator, when you type the log, it'll automatically ask you for a base. If you want to skip over that and just type in the 25 up here, leaving this blank, it'll automatically fill in a 10 for you. So when you've done that, let's compare answers. Should get about 1.4, which is what we would expect because 10 to the first is too small and 10 squared is too big. So it's got to be a number in between 1 and 2. Some of the answers are so obvious that kids get stuck on them. On the next one, it's still a base 10. We're still raising to an unknown power like x, and we're trying to get to 10 to the 27th power. All log problems involve trying to find that missing exponent. So in this case, the exponent is staring us right in the face. The 27 is the missing exponent, and they gave it to us even before we started. The next one tends to be tricky for kids as well. It is a base 10. We're raising to an unknown power x, and we're trying to get to the 5th root of 10. This is where kids get stuck and kind of go, huh? Well, I would recommend that you reach back into your brain and try to remember another way to write taking the 5th root of something. It's why we covered roots and rationals in the previous chapter. Taking the 5th root of something is the same as raising it to the what? That's right, 1/5. So now we're back at the situation we were in earlier. If you have a base with a power, the power is what you're looking for. This guy's missing his power, this guy has it, their bases match, so 1/5 is your final result. Don't be fooled by a question like F. The base is missing but nothing else is. So when you raise it to the power, don't assume that we're raising to the x. We're always raising to whatever the log is equal to. So in this case to the 4.2. This would have been a graphing calculator question. I would allow you to type that in on your calculator to get an actual numerical answer. You should get about 15,848. I apologize, I didn't mention calculators on the previous ones. This one would have to be graphing calculator, and then these two would both be baby calc. Sorry about the mistake. Let's try some logs with other base type questions. Basically, you're going to handle it the same way, but there'll be less for you to fill in. 2 is the base, the power is what we don't know, and we're trying to get to an 8. Hopefully students have that one memorized, just like they have 3 times 3 is 9, 2 times 2 times 2 is 8, so it took 3 of them to get to her. Similarly for the one right next to it, if I take 6, raise it to a power, and try to get to 776, I'd have to do some definite trial and error there. I know it's going to be bigger than 3, because that's only, it's just not enough. And though, so I know that it's got to be a little trial and error here, I got a 5. On the next one, the base is what's missing, so if I rewrite it in exponential form, I get x to the 1/3 equals 10. To try to get rid of that fraction power, I would want to raise to the reciprocal, which would be 3 over 1, or just simply a 3. Taking the taking the power of a power, 2 powers together, they get multiplied together. 1/3 times 3 ends up being a 1, so x becomes x to the 1. And then 10 to the 3, that's just going to be 1,000, and that's your answer. Similarly for the next one, the base is unknown, the 15.2 is the power, and I'm trying to get to 8. To try to get the x isolated, I have to raise it to something. But normally fractions and decimals don't go together, they don't like each other, but we don't have a choice here. We need the root of 15.2, so we're going to raise to the 1 over 15.2 power. That crosses out all threats on the side where x is. Over here you literally got to type that in and see what you get. and I believe you get 1.15. On the next two, they'll behave very similarly to each other. By the way, this would be graphing calc on the one we just did. This one would have been baby calc, this one would have been baby calc, and baby calc. On the next one, if you rewrite it as exponential form, we get 8 to the x equals 1/8. Hopefully you remember from earlier in the video that when the base flips over, it has to be negative. If the value of the number doesn't change, then it has to stay a -1. Let's try that one more time with our last one here. If I set it equal to something and say 4 to the x equals 1/64th, I got to figure out 4 to the what is 64, and then I got to remember to make it negative. So let's see here, 4 to the -3 is the 1. We've got two more problems to go here. If you're asked to solve, we will learn official solving techniques or revisit them in lesson 9.6. In this lesson, you're not really solving anything other than finding whatever's missing, but you won't use traditional algebra to do things on both sides. We'll do that in lesson 9.6. What we're going to do here is just rewrite it in exponential form. So I'm going to use log base 3 of 57, and that should equal an x, because the exponent has to be the answer. So that's as far as you can go. If you have a TI Inspire calculator and you're allowed to use it on this one, you could type in log base 3 of 57 and actually get a numerical answer. On the next one, it just says evaluate, so it's not really a solving question, but it involves a little bit higher order thinking here, so I wanted to put it in this section. If I rewrite this in exponential form, I'm going to get 4 to the x equals 8. Again, to get rid of the the exponent that I don't know, I need to undo it somehow. Unfortunately, there's no way for me to undo that like I did on a previous question where I used a reciprocal. Using a reciprocal here is not going to help me. So what you want to do in this situation where you're asked to pull forward but you don't know how without a graphing calculator is to identify a base that these have in common. Hopefully what rings a bell there is the number 2. 2 squared is 4, and 2 to the 3 is 8. The problem is there's still this x lurking around and getting in our way. So let's just focus in on the exponents for a moment. 2x has to equal whatever's in that bag at 3. So let's divide both sides by 2, so we get 3 over 2 as our final answer. And don't forget, the answer to a log problem is that's right, exponent.